Hello and welcome. So we are studying how to use op-amp based amplifiers to make different types of voltmeters, electronic voltmeter circuits. Okay, and all these were analog electronic voltmeters, not digital. So the last example that we took, it was of a precision rectifier. Okay, so the beauty or speciality of this circuit is how we put this diode or rectifier in this circuit. Okay, instead of putting it here, if we had put the diode here, then there will be some voltage drop across the diode which will cause some inaccuracy, or we have to take that into the calculation. But if we put it here, the op amp itself takes care of this voltage drop. Whatever the voltage drop across the diode is, the op amp will increase its output by the same amount more, so that this diode voltage drop doesn't come into effect at all. Okay, so that's what was the beauty or speciality of precision rectifier was. And in this way, so we have taken different examples for AC circuit, DC circuits. So this was AC half wave rectifier. Previously, while discussing DC circuits, we have talked about voltage to current converter and a lot of different things. So let me just take another example today. Another new circuit. So the point I want to stress on, highlight, is that these circuits which we are drawing are not exhaustive sets, are not all that one can do with this. Okay, so if you think, if you invest some time, you will come up with new circuits, newer ideas on your own, and you will enjoy the subject, I guess. So let us take a circuit, an AC voltmeter, AC electronic voltmeter with full wave rectifier. Okay, so what can we do? Let's take some simple idea and then we will refine it. Okay, so we have a voltage, unknown voltage to measure, call it Vi, and then we assume this is small, so we will amplify it. To amplify it, we can take inverting or non-inverting amplifier. Let's take a non-inverting amplifier. Okay, so I'm taking an amplifier, non-inverting, so I give a negative feedback, so a fraction of the output goes to the minus terminal. This is the input of the amplifier, so I can connect the input voltage to the amplifier input. This is the output of the amplifier, VO. This is grounded. Okay, so this is the output voltage, and if this is AC, definitely then this is also AC, and if this is R2, this is R1, then you know that this is given by 1 plus R2 by R1 times Vi, but this is AC, and now we can measure it using a AC voltmeter. So this has to be a AC voltmeter, simplest solution. So it must be AC voltmeter, like electrodynamic. Okay, we cannot use PMMC here. But if we want to use a PMMC instrument, because we know PMMC instruments are often higher, more sensitive, than this electrodynamic, and the scale is also linear. So if I want to now use, if we want to use PMMC meter, then what we can do is this. Okay, so we if it is a PMMC meter, then we cannot connect directly like this because this is AC voltage. So what we can do, we can take a rectifier, and we would like to take a full wave rectifier. Okay, so what we can do is this. So let's first draw a full wave rectifier. The bridge I shall draw first. Okay, so this will be the input of the bridge. So I would say like to have the current like this in this direction. So I will put the rectifier, the diode, in this way. Then here I shall put my meter. Okay, and here I shall have the other diode. So you see, in the positive half the current will go like this, and in the negative half, when this side is at higher potential, then the current will go like this. So this is my meter, and this is a PMMC meter, PMMC voltmeter. Okay, fine, we can use this circuit because now you see the voltage here is AC, but the current that flows in it is DC. It is full wave rectified. In one cycle it goes like this, and in another cycle it also goes like this. So through the meter, current always flow from left to right. Okay, and we can control the range of the meter with a suitable series resistance. If you want to change the range of the meter, you can add it here. In theory, you could add this resistance also here in this circuit, because it will finally come into series with the meter. But now you observe the small problem in this circuit once again is that the voltage drop across diodes should be taken care into the calculation. Okay, otherwise there will be some drop here. If we ignore that, then the reading actually that we will get across the meter will be less than what is here. So we will have some error. So in this circuit, in the above, means this one, above circuit, the diode, the forward voltage drop, forward drop of the diodes causes inaccuracy if we do not take care into the calculation. So now what we can do, okay, so we will modify it. We will modify this circuit and try to make a circuit so that this diode drop doesn't affect. So let's try to make a modification. You know, the idea is essentially to put this part, I mean, somewhere here. Okay, so what I will do, let me take this rectifier bridge with the meter and see, let me first keep it away. Then I will make some space. Okay, and then okay, this is connected. Then I will put this actually here. So I open this part. I bring it here. And I wish I could rotate this, but I cannot rotate it, so I connect it like this. Okay, so you see the current will flow like this in the positive half through the meter from left to right, and will go like this. In the negative half, current will go from here again left to right through the meter and like this, and will enter this. Okay, so this is a full wave rectifier circuit because current through the meter is always from left to right, both in the positive cycle and in the negative cycle. Okay, so here the diode drops, doesn't matter. So this is very important to note. Okay, and you also observe that this is actually a voltage to current converter. So this circuit is a voltage to current converter. Why? So you observe this is at voltage Vi input. Due to virtual sorting principle, this potential will also be Vi. This is time varying, call it T. This is also T. So at any and every moment, ideally, this point will be at the same potential as this. Okay, this is due to virtual sorting. And so here I can write this point is at VIT, right? If this is at VIT, then this current I can be written as, this is same as Vi divided by R1, right? So this is this current, and the same current must flow through this, which means it will eventually flow through this meter, and definitely this is a PMMC meter. Okay, so this current I is the same current which flows through the meter I. The only difference is that here this is purely AC, but this is half wave rectified. Okay, so let me call it I prime. Okay, I prime is the half wave rectified version or form of I. Okay, I is AC, I is, so if this is I, then I prime is definitely this. This is I prime. Okay, now can we take a numerical example on this? Okay, let's take a numeric example for practice. Question: suppose let's take R1 equal to R2, or okay, let's take R1 is equal to 10 ohm and meter reading is equal to 1 milliampere, then VI RMS is equal to how much? So this is the question. Okay, so we have the circuit and circuit parameters are given. Okay, R1 value is given, R2 value is not given, but we shall see R2 is not required. And so the reading of the meter is given, how much is the input voltage. Okay, so I mean that's how we should use a voltmeter, right? We observe the reading of the meter and from that we have to specify the input voltage, or we have to estimate the input voltage. So we know 1 milliampere current is flowing through this. Even it is not specified explicitly, this 1 milliampere is average current, okay, because this is a PMMC meter and PMMC meter shows only the average value. Okay, so although solution, although not specified directly or explicitly, meter current is 1 milliampere average. Okay, meter current which is full wave, sorry, I made a mistake, this is full wave. Meter current which is full wave rectified is 1 milliampere on an average. Okay, so this current, the average of I prime is 1 milliampere. Okay, so what can you say about the peak? So I prime peak divided by pi by 2, this is the I prime average. Okay, average value of meter current which is 1 milliampere, and from this we can write that I prime peak is equal to pi by 2 milliampere, right? So the peak value of this current is this, right, which also flows through this, and therefore, and you see I and I prime, they are just, one is AC, another is half wave rectified, but their peak value of I and I prime are same. So from this we can write I peak, okay, peak value of this current should also be pi by 2 milliampere, right? And if so, then we can write I RMS should be this divided by root 2 . Okay, and so this is the RMS value of this current. Now if we call this voltage, this voltage is same as VI, right? So this voltage, or if you call this point A, then RMS value of VA or RMS value of VI should be IRMS multiplied by R1 resistance. So this is nothing but R1 is 10, okay, so 10 multiplied by pi by 2 root 2 millivolt, and you can compute how much is this. Okay, so this is how you can do it. So this is a full wave rectified voltage to current converter, and this way we can measure the unknown voltage by observing the reading of this meter. Okay, So I guess I have talked enough about voltage measurement. I will now talk about current measurement with op-amp based amplifier circuits. Okay, so now let's talk about current measurement. Okay, suppose I have a network or a circuit, a complicated circuit, and one of its branch is AB, and through which the current IAB is flowing. Okay, and I want to know how much is IAB. I want to measure this current. Now the usual way we measure it is by inserting an ammeter in the circuit. So let me insert an ammeter. Now this ammeter can tell me the value of IAB. But there is a problem. The problem is that the ammeter has some internal resistance, and the moment you insert this internal resistance in this circuit, in this branch where no resistance was there, so the resistance is increased, so definitely the current can change, the current can decrease, right? Okay, and the more the internal resistance of the ammeter is, the current will decrease more. So therefore, the value that we will actually measure will not be same as the current which was there in the absence of the meter. So the problem is the non-zero meter resistance, ammeter resistance, will change the value of IAB during measurement. Okay, so if I want to measure it, I insert the ammeter, but then the current changes. So how can we get rid of this problem? The only solution is the resistance of this meter should be as small as possible. Okay, so we should insert as small resistance as possible. But you know, if it is a PMMC meter or any electromechanical meter, it is made up of a coil, and the coil has some resistance. If you want to decrease the resistance, then you either have to make very big thick coil, I mean thick you have to take thick conductor, and the meter will be big in size, huge in size, costly, which is not feasible. And else, if you reduce the number of turns of the meter, then also the resistance will be small, but then the sensitivity of the meter will be very low. So what we shall do is this: we shall insert a small resistance, so a very small resistance, as small as possible, and then we shall measure the voltage across this resistance by amplifying it. So we shall take an amplifier, and here we shall have a voltmeter. So you see, this is a very small resistance, as small as feasible, considering other factors, of the order of maybe 1 ohm, 2 ohms, several ohms. But if we, if we take a small resistance, then the voltage drop across it will also be small. Particularly if the current that we are measuring is small, then this voltage drop will also be small. And therefore, to measure it successfully, accurately, we must amplify it. So, but this is the scheme, right? So this is the scheme, and you see this is my so this is the measuring instrument, current measuring instrument. Which is made up of all these things together. Instead of just one ammeter, we have all these things together. But the input impedance, okay, if I just call this resistance as R, the input impedance of this meter or instrument, okay, which is made up of all these things together. So input resistance is how much? Can you guess? This is nothing but R. Why? Because input resistance is nothing but the ratio of the voltage between these 2 points. Okay, so these are the input terminals, which is same as these two. So this voltage divided by this current should be the input impedance, and you can assume that an ideal amplifier should have these currents here equal to 0 or negligible. Okay, an ideal ampere should not take any current or much current, so this current is negligible. So this current, if you call it IAB, it flows almost through this resistance R. So this is also IAB. It flows through this resistance R. It doesn't go to the amplifier. That's the beauty of an amplifier. That is one of the necessary property of an amplifier, that it should not take any current. It should not draw any current or draw minimum possible current. Okay. So now let us draw maybe a circuit. So we shall draw a op-amp based circuit. So this is the circuit that we want to measure or probe. So this current which flows through this branch AB, call it IAB. We want to measure the value of IAB. And here we have a small resistance inserted, call it R. Now this is one part of the circuit. Another part will have the amplifier. So let me draw an amplifier, whichever amplifier you like. Okay, I shall take a non-inverting amplifier. I like that. So this is a non-inverting amplifier. And suppose we want to measure the output voltage. So we put a voltmeter here, right? So this is a non-inverting amplifier. So this is the voltmeter. So this is the input of the amplifier. This is of course the voltmeter, this is the circuit, this is the small resistance. Now there is a big question, how do I connect it? Because you see I want to measure the voltage between these two terminals A and B, and my ammeter as I have drawn has only one input. So can you guess how should I measure this voltage? Basically this amplifier measures the voltage applied at this point with respect to the ground. So what I have to do, I can connect one of the terminals to the ground, okay, and the other terminal here. Okay. So assuming there is no other connection between this circuit and this circuit. Otherwise, we may short circuit something. Okay, so so assuming that there is no other connection between this part of the circuit and this circuit other than only these two red lines. Okay, so this is the way to measure it. And if you want a bit more detail, I shall put it, say how to connect this power supply of this amplifier. So say I have a plus minus 12 volt power supply. Okay, so then this is the reference point, ground. Better I shall draw it this way to indicate that this is just a reference point and this is possibly not connected physically to earth. Okay, we don't have to connect this to physically to earth. Okay, and so this power supply goes here. This is V supply, plus V supply and minus V supply. Okay, so essentially this is the reference point, which is, so it actually means this point and this point are actually connected. If I put same symbol in three parts of a circuit, that means these are actually connected. So you can think that, not think, it is really that these are actually connected. And this point is connected to this. Okay, so this is current measuring circuit. Okay. Great. Now so we shall I think we have enough examples. If you need more examples, if you ask for more examples, please go through the textbooks suggested. If you need any help, ask us in the forum. We shall we will be happy to make more videos on this and share with you if you want, if you need. And so we shall stop this topic here. In our next class, we shall take up a new topic, which is instrumentation amplifier. What is instrumentation amplifier? That is again an amplifier made up of op amp, but not one op amp. That is made up of several op amps, 3 op amps maybe. And we shall see how that offers simultaneously more gain than one op amp can offer, and also very high input impedance. Okay, and then once you learn that circuit, that instrumentation amplifier circuit, in principle all the circuits that we have studied in this chapter, you may modify these circuits in this chapter and replace these single op amp based amplifiers with the instrumentation amplifier in principle. Okay, I may have to do some tricks for that. I request you think how to do that. Thank you.